All right, welcome back. So I want to spend the next couple lectures finally talking about deep learning. I've forecasted this for a long time. It's a funny thing to teach these days because some of you know it extremely well and some of you haven't really played with it at all. And there's also like a massive amount of resources online, so it's actually pretty easy to learn if once you commit yourself to that enterprise. So here's the way I'm going to try to do it. I feel I have to say a few of the fundamentals. I'm not going to talk about what is a neural network. I think everybody knows roughly that, but I'm going to make sure that we talk about some of the basic concepts of computer vision, but mostly targeted towards how they're used in a manipulation pipeline. So that's my filter for how to not talk about all the things is to really dial it in for manipulation. Okay. So we've done perception, with geometry already. And if you remember, even in the sort of antipodal grasping unknown object case, we had a pretty good solution, but we left a bunch of things on the table, right? So there was really no understanding of what an object is, right? Which manifested itself when you just run that clutter clearing example on real systems or even simulated systems. You'd often pick up two objects, or you might pick up a hammer, like on some part of it, just not understanding anything about the mass, and then it's going to rotate out or fall out of your hand. You really, in the antipodal grasping pipeline, you really need cameras around to avoid having just partial views. You need to be able to see both sides of the objects. Otherwise, you have to somehow hallucinate what's at the back of the object to even find your antipodal pairs. Our depth cameras don't work directly from transparent objects. RGB is a more powerful sensor for that. And sometimes you actually just have tasks that are fundamentally, require you to say, I don't want to just pick anything from the bin. I want to pick the mustard bottle out of the bin. Right? So there's a lot of things that we must do something more than what we've done so far to accomplish. And for some of these, I think learning is fundamentally the right way to do it, because the only way you really, if you don't have enough information from your instantaneous sensors about what the back of the object is, fundamentally the way that you fill that in is by having some experience with the different distributions of objects and how they fall and land on each other. And it really is somehow a statistical problem of what is likely to be behind the object, given all the things I've seen in my life. All right, so that's where learning comes in very naturally. And of course, deep learning works incredibly well and has powered a lot of changes. OK, so like I said, let me try to take a sort of a fast cut through the sort of computer vision 101, trying to get us with the same vocabulary to the manipulation use cases. OK. How many people feel like they know basics of computer vision in the deep learning era, right? So some, definitely some. Good. OK, so the way we're going to do better, and by the way, everything we did so far was using the depth channel of our camera, but we're even simulating RGBD cameras, right? So today we're going to finally use RG and B, all those other channels, because they're super valuable, right? All right, so of course, the basic operation today is we're going to take an RGB image in. We can talk about adding depth as an extra channel later, but let's start with just the standard RGB input. We're going to shove it into a deep neural network, okay? And we're going to get something out the back. And that actually, a lot of the interesting questions that we'll get into is what is the right thing to ask to come out the back for a manipulation context. Okay, but the classic one is some sort of a classification of what is in the object. So for instance, you might say, what's the probability that there's a dog in the image, or there's a probability there's a cat in the image, or an elephant in the image, right? Okay, and then you have an object classification problem, which just takes an image in and says it would maybe pick the highest probability output and say that's my recognition. Okay. Now it's really interesting. So I'm old enough to have seen all this happen, right? So and I remember, when people they had success with these kind of models, and they were small neural networks, and they were a small list of categories, right? And I remember, Jan LeCun is a friend, and he used to come by and do his demos, and I'd be like, yeah, that's cute. You could do that for 10 categories, but you're not going to do that for all of WordNet, right? Yeah, I was wrong. You can make this list extremely long, right, and organize it very carefully so that the ability to recognize categories extends to extremely big models and extremely diverse outputs. Okay. So even though that looks like a limiting picture when I draw it like that, it's proven to not be. Right, and so of course the language here that is most similar to what I've been writing in class is that I'm taking an input x, coming to an output y, and I have some parameters, my neural network parameters here, and given a data set of pairs, I'll try to minimize, by finding the theta that minimizes something like sum over I of yi f theta xi squared. It actually looks a lot like the least squares problems we've been solving in class, but of course the nonlinearities in f in the neural network make it a harder problem to solve in general. With the convex optimization tools aren't really applicable, and you're going to do gradient descent, stochastic gradient descent on that. Okay, so what happened between the initial demos of small neural networks and small numbers of categories with small data sets, right? That's where it was in 2010, let's say, right? The first thing a number of things busted that open. One of that is compute, not to be just GPUs, made that a lot bigger and a lot better. Architecture's a little bit, okay, but I think most people would agree that the biggest thing maybe was that we got some really big curated data sets, right? And ImageNet being the most famous. I guess this was released in 2009. These days it's 14 million images. And they're not just images, they're carefully curated images with categories that were thoughtfully selected from the WordNet, sort of a reasonable dictionary and taxonomy of words that you might want to have output. And I think the scale and the quality of that data set really started unlocking people's thinking and the success of these models. Okay, so ImageNet was extremely good for object classification. You just say, I've got an image, what is in that, what's should I label that as a dog image or a cat image? Okay, but it's important to understand that the field sort of identified a handful of different problems to focus on. Image recognition being the one I talked about so far. Slightly richer than that is object detection, right? Where you not only say this is a sheep image or something like this, but you actually say here's a sheep and here's a tight bounding box that identifies the location of that sheep in the image. Richer still than that is semantic segmentation, where you now have a pixel-wise label, okay, and you mark all of the sheep the same color pixel, the dog a different color pixel, and then the instance segmentation is sort of the next level beyond that. So image recognition by itself was fueled by ImageNet, but it's actually not quite enough to be super useful for robotics, right? But when you get all the way to instance segmentation, then that is already enough. We're going to be able to do computer vision tasks that are beyond this, that are more specific to manipulation. But if you only took an off-the-shelf computer vision system that was trained to do image instance segmentation, then you're already in pretty good shape. If you wanted to, for instance, look in a cluttered bin, say I want to pick out the mustard bottle, right? Then this would allow you to take a set of RGBD point cloud, pixels coming in, filter out the ones that are related to the mustard bottle, project those back into 3D, for instance, and then choose an antipodal grasp that could pick out the mustard bottle. Right? You can build complete pipelines by just getting to the level of instance segmentation. Actually, another thing that people have commonly did when this started to work really well was they would, they'd do that same beginning of the pipeline. You'd take your RGBD images, you'd extract out the ones that mattered, and then maybe if you had a known model of the mustard bottle, remember we said ICP, the iterative closest point algorithm, didn't work if you just put it into, if you just give it a messy scene and ask it to find the mustard bottle, you've got no chance, okay? But if you segment out just the pixels of the mustard bottle and now run ICP, then segmentation plus ICP is a pretty powerful pipeline for pose estimation. We have better pipelines now, but that was right out of the box a pretty good thing. Okay, so you guys got to give me feedback so I can speed up or slow down. Yeah. In that case, you would need to know the geometry of the mustard bottle. Yep. So if you're looking for known objects, then ICP would be viable. Right. The antipodal would work for unknown objects. Yep.
How do you combine segments from different cameras?
Yeah. So good. So this is the segmentation right out of the box of a computer vision will be a 2D image segmentation. So you have multiple cameras looking. Each one you label a pixel as being part of the mustard bottle or not. You project that into 3D, and then when you merge your point clouds, this is the most naive implementation would just be you only merge the point clouds that are associated with the mustard bottle into the 3D representation.
Okay, but I'm talking about instance segmentation. So if you have storm mustard bottles, how do you associate segments from one?
Yeah, no, you're right. That's harder. You have to somehow solve a correspondence problem to understand which in this camera, which instance is in this camera. If you have multiple instances, that's true. Yeah. Okay, so the ImageNet actually didn't unlock instance segmentation. The data set that did that was the COCO data set, which was MS COCO. It came back a little bit, it came out a little bit farther out, and it was much smaller data set, but much more detailed labels. Can you imagine, having getting people to label every pixel of these images in great detail? Thousands and thousands of images. It's actually so Antonio Torralba, who's one of the faculty here, he was one of the first people. He made some of these labeling tools, and it was interesting to hear him talk about this, 15 years ago. And he's like, people are insane when you ask them to label an image, and you say, I'm going to pay you 2 pennies on Mechanical Turk, right? And they will spend like a half hour getting every detail right. It's like, that's crazy. That's just, I'm only paying you like 2 cents. But then people are almost obsessed with getting it right, he said. And they found ways to scale this to unlock instance segmentation, I would say, with the MS COCO data set. And it's interesting. So MS COCO did not have as rich of a list of categories as ImageNet. Okay, it had I like sort of finding the list here. So there's person, bicycle, motorcycle. There really are like elephant, horse, sheep, bear, zebra, giraffe. All very fun categories. But if I have a robot arm and it's looking in a bin, I don't really need to identify elephants, right? And unfortunately, that list is only so finite. A lot of the things that I care about doing manipulation on aren't actually in the list. Okay, so yay for identifying elephants, instance segmentation. But I'm going to have to do more if I want to apply this to my domain. Okay. And the thing that really I think the field legitimately didn't. Maybe someone did. Maybe Jan or other people really saw this coming, but everybody was talking about transfer learning. There were funded projects about transfer learning, like how are we going to eventually do transfer learning? And then it just kind of happened on accident. Okay, and so the thing that somehow happened by accident was it turned out if you train your computer vision pipeline on ImageNet and COCO, they seem to be big enough and diverse enough that training on them first on a big data set first, and then giving it a little bit of a data set second, was enough to get a lot of the robustness of being generally good at perceiving images and do pretty well on your in-domain images with a small data set. Right? So not everybody else, if I want to apply it to my set, I don't have to make something as big as ImageNet to make that work. Right? I need to just collect a small number of images and then use pre-trained weights from ImageNet. Yeah. We're gonna talk about that. Yeah, yeah. So, yes. So that's a huge thing. And the most standard way to do that, of course, would be to, which is sort of natural. If you think about the architecture of a deep neural network, okay, which has the image coming in and many layers of the network, it's not until really the last layer of the network, or maybe some last chunk of the network, that it actually starts having the concept of dog or cat or elephant baked in. Of course, maybe we don't know exactly what's happening in the weights. You can inspect them, whatever, but the thing that must change is the very last layer. You need to take your dog output and turn that into a mustard bottle, and your cat output and turn that into a Cheez-It box, right? Because we only pick up YCB objects in this class, right? So the simplest thing to do is really just to take off that output layer, leave all the previously pre-trained input layers, and put on a new output layer, and now take your new target data set and start training again. You can potentially freeze this data set. There's some cases where people will do that and to be effective, but in general, you'd let these layers adapt too, and you'd expect this part to have to train from scratch. Okay, but this changed from now having to get 14 million images for my in-domain thing to maybe I have to pay, there's a bunch of startups that came up, all sprouted up at the same time. Like, we're going to have a data labeling company, right? And you can pay them to label 1 to 10,000 images of silverware. We actually did pay somebody a lot to identify silverware because we wanted to pick up silverware for the dish loading thing, right? And there was there's this business model that grew up around just generating that last set of labeled image data at the segmentation level, right? Yeah, so that's one option. Maybe you pay a startup to do it or something, okay? But roboticists tried to figure out more effective ways to make that data, right? To not pay. Maybe we're creative, maybe we're cheap, I don't know, but we found other ways to try to label that data. One of them I mentioned to you once before, and it's actually a pretty nice example of this, right? So if you remember when I was talking about ICP, the problem with ICP being applied to this sort of global data set was that it's just got no hope of solving the global correspondence problem. Okay, but this pipeline, this label fusion pipeline, was one of a handful of approaches that were kind of like this that could generate a lot of ground truth training data for an instant segmentation. And the way it did it is we would move a camera around the scene, okay, generate a 3D model of the scene. Those tools have gotten even better with NeRF and Gaussian splatting and everything like that now, but already we could build a nice model with elastic fusion. It was in those days, okay? And then in that 3D point cloud, we would have a model of, let's say, the drill, and we would ask the human to click 3 points on the drill model, 3 points on the point cloud, and that would solve this hard global correspondence problem, but take very little work from the human. We would snap the drill into position with ICP, and then we had not only one image that was perfectly labeled by rendering it back out, but all of the images that we took of the surround sound would be somehow immediately back projected and had great ground truth labels. Okay, so by doing things like this, we could quickly generate a lot of in-domain data for handfuls of objects that we cared about. The other approach, of course, is to try to generate ground truth labels in simulation, right? In our RGBD sensor simulation, in the cases that we already showed, remember there was already an extra output which said label image. And if you plot that label image with a proper NumPy color scheme, you have to do a little mapping to make it colorful like this. Otherwise, it would be like color 0, color 1, color 2, and they're all, yeah. But okay, with a little bit of remapping of the colors, then you'll see pictures like this, where every pixel has exactly the ID of the object in the data set. Okay, and you can just generate as many images as you want this way, right? So it's been really interesting watching the progression of how people build these extra data sets now. Okay, so if you were to say render images that look like this, and then point a real camera in the real world, then you would probably be a little suspicious that training on this kind of image would be successful in the real world. Okay, so people took a couple different paths there. One of them was to bring in better and better renderers. So if you see in Drake, there's actually multiple different renderers. We have like the OpenGL renderer, that's this one. We have a VTK one, which is just a little bit better, okay. But then we also have the ability to send it to Blender to do rendering, okay. And so now you're doing, and Blender has a few other rendering options, okay, but you can choose a photorealistic renderer that's doing full ray tracing. It might take a second per frame, but if you're doing offline data set generation and you want to have the most realistic possible data, then that's a time I would be willing to spend. Right? The hard part still in that simulation pipeline is generating rich enough assets. So in order to get the quality that you'd expect out of Blender, right, then you actually have to have the material properties be set properly. And that sometimes requires an artistic touch that I don't have, but I have friends that have, and you might need background material, background illuminations and things like this to make it relevant. Okay, so there's been a series of work of people showing that sufficiently high fidelity rendering could, especially when mixed with a little bit of real data, you could train a system almost completely on simulated data and have it work in the real world. But there's also been an incredible amount of work now that worries less about the quality of the renderer and starts throwing in much more random perturbations, right? So domain randomization is the generic term for it, okay? But you can imagine rendering my scenes not only with the original simulation assets, but starting to throw down all sorts of different textures, all sorts of different lighting conditions, all sorts of distractors. This example doesn't actually have distractors. We had, when we were doing the silverware project, it was, you'd see like a bin full of silverware, right? And then you'd see like an elephant, in the middle of it, because you knew the real system was going to have occlusions. So how do you do it? You take random crops from random images and you stick them in the middle of your image just to simulate an occlusion, badly, admittedly. But you'd see like elephants and clowns and spaghetti or whatever, like there's random things that would just be stuck in the middle. But beyond, I think, expectations, having even simple renderers with enough generalization in the things you don't care about and enough data often allows people to say, I'm training only in simulation and I have incredibly good performance in the real world. Okay? So there's kind of a mixture now of like get a little bit of real world data, generate some really high quality stuff, or just generate a whole bunch of low quality simulation assets and force the system to pay attention to the things that you care about by changing wildly the things you don't care about, like the background image. Yeah? Yeah, for sure. I think that so you can definitely use, like having enough assets to generate diverse training data is one thing. Assuming that you're going to find exactly those assets at runtime is a stronger assumption, right? So I would say that you could train a system that would pick up lots of different objects without explicitly assuming that you knew the models of those objects, right? So it's just different levels of assumptions that you're willing to make about the task. Yeah, but absolutely, the more you model, the more you can dial in your trajectory planning and everything like that. Yeah.
Yeah. So related to that, how important is it to dial in the distribution
so good question. He says, so the domain randomization, so the ideal case in some sense in machine learning is that the distribution of test data, right, in some arbitrary dimension, you have some probability of data, which would maybe be my training distribution. This would be my probability of X, and then I have some other test distribution. And you'd love for your test distribution to be, somehow inside. I guess it can't be small; it's normalized. Okay, you'd like it to somehow be completely covered by your training. If you could make them identical, that would be the best. Okay. Yeah, I think that the picture that you'll see in this domain randomization workflow is that the training distribution is massively wider than the actual real distribution. Like, I don't put leopard prints on my dishes or something like this. I don't have elephants flying in front of my silverware, okay? But somehow, I think when the tasks are relatively easy, then you don't need to be narrow and focused. Yeah? I think as the tasks get harder, both in control and in perception, then you're going to have to dial in the details more generally. We've done projects that have looked at perception systems that were, let's say, deployed on many robots in a fleet. And there's a big question of, do you specialize your training to the specific member of the fleet, or do you share the data across the entire fleet? And at some point, you do win by specializing, by trying to train a model that's more specific to your immediate data set. But it takes a long time. You actually do really well in most perception tasks by just sharing it. More data is better. Yeah. And I think domain randomization is really the extreme. The type of domain randomization you see they can be really bizarre. Definitely not in distribution for the real world. It's hard to get the nuanced distribution of the real world. Okay, so let me talk through just a little bit of the details of how one of these pipelines work. Mask RCNN is one of the standing instance segmentation pipelines, and I think just seeing a few of those details will help you see the way these. I don't want to go into the architecture too much, but the way that things are input and output are structured, the way the training is structured, you can use it immediately on your projects. Okay, and then we'll talk about. It actually had an incredibly good reign. Like it came out in around 2016 or something like this. And in the age of deep learning, where every month your newest result is eclipsed by something better, Mask RCNN was like the best instance segmentation until like April of this year, maybe I'd say. It probably finally lost its title. And I'll tell you what the thing that beat it. Okay, but it's an extremely good, simple, clean architecture that you could definitely use. And I have examples in the notebook of training based on the Drake simulated cameras, Mask RCNN segmentation. Okay. So to do that, let's just talk a little bit about how I would take this very basic model of an image coming in and a probability of being a dog, a cat, an elephant coming out, and give a more rich output, right? So instance segmentation would say, I have first of all, a variable number of outputs. Where does that come from? This network has just a fixed number of outputs, okay? A variable number of outputs, one for each instance in the scene, and now a very high dimensional output, a pixel-wise label, right? If I'm going to do, if my output, this problem is easy. We understand the output. This problem, we just have to think. If you haven't done it, you just have to go through a little bit of a mind shift to say, like, how does a neural network output something like that? Where not even the number of categories or the number of instances is known to the network. Okay? So we can do it in a few steps. And I'll give the example of mask RCNN. Okay, so the simplest way to go from an object, an image recognition system to an object detection system would be to just take a lot of different sub-pictures inside your image, and for each one of those, this would be like the sliding window would be the simplest version of this, right? If I run object image recognition on every one of those boxes, and then I just return the box that has the highest recognition, then I could imagine having, first of all, a variable number of outputs and an output that told me the bounding box was right there. Okay? So in practice, when mask RCNN is running, it's actually, it's not doing this exactly. It's doing a smarter version, much smarter version of this. But it's actually running, evaluating effectively an object, an image recognition system many times on many different regions, okay? And it evolved in a series of sort of steps. It went from basically convolutional networks, right? ConvNets, which was for the image recognition, image in, recognition out, to RCNN, which was regions with CNN features, okay? And instead of doing, image just a sliding window, because actually even the sliding window isn't sufficient, right? If that box didn't exactly line up with the car, you don't know how big it should be, how small it should be, so you end up having to do many sliding windows of many different sizes, and that starts getting really expensive, okay? So people used, for a while, RCNN used some classic machine vision ideas, looking for features and the like, to try to have region proposals. So instead of just searching for arbitrary boxes of arbitrary sizes and trying them all, it would try to propose particular things just based on sort of classic computer vision features. And then for each one of those boxes, it would, in order to use the same size network, it had to sort of squeeze and shrink, and rescale that box, okay? But then it would be a more classic CNN in the middle, okay? Is it an airplane? Is it a person? Whatever. And that already got us to a point where we could start doing, better object detection and bounding box estimation. The next step was making it faster. Okay, so it was actually, the paper's called Faster RCNN. And basically, the story of these things is always, if there's a module that is not learning yet, then it will eventually be pulled out and replaced with something that's learning. And so the part that was still not learning in the RCNN was the region proposal. So now there's a network that's actually proposing the regions. And then roughly the RCNN somewhere in the middle, okay? And then after it identified the box, you found an object in the box, then there's one extra step that it was introduced at Faster RCNN, which would actually just say, I want to actually adjust the box to be a tighter bounding box. That way your region proposals didn't have to be perfect. You weren't just going to output the proposed region again. You could actually say that if my proposed region was here and my, I don't know, horse, something was here, right? Then I could actually say, here's a tighter bounding box. So it output four numbers, to just pick a tighter bounding, a refined bounding box as an additional output. And that gave us these detection bounding box windows. Okay, and then that's mostly it. I think the papers, so people have the impression that, in deep learning, you take lots of random ideas and you put them together and some of them work and some of them don't work, okay? But actually, if you look carefully, and I had a good friend who really convinced me of this at a time of, where I was like, what's happening here? He says, if you look carefully, there's actually a handful of people, authors, and a handful of architectures that have had dramatically more, most of the impact in the field. And they're actually, the architectures are not arbitrary at all. They're actually very carefully thought out, often very simple, okay? So I think mask RCNN was successful partly because of that. So it did the effectively faster RCNN, and then it did one extra thing, which is to now bring the pixel-wise labels in there, and that was just bolting on sort of one more piece. FCN is a fully connected network, whereas a CNN takes a big image in and puts like a detection out, a small number of outputs. If you want to output something that's the size of your input, then you use a fully connected network, FCN. Okay.
Well, you can use a UNet.
You can use a UNet too, yeah. FCN was the first popular one. Yeah. And again, reigning champion for a long time. UNets have had a lot of success too. I mean, in diffusion, people use UNets a lot. Mm-hmm. I think it's fully convolutional. Yeah. Did I say it wrong? I bet it's possible I said it wrong. Yeah. Good. I might have said fully connected. Yeah. Okay, so I mean that's a crash course in mask RCNN. I don't know, any questions about that? Some of you probably have used this more than I have, but what do you think?
When was this?
I think 2016. Does it say anywhere here? It was pretty early in the process, maybe 2017, something like that. Surprisingly long reign, right? Okay, so should we play with it a little bit? I have it implemented here. So if we want to, for instance, take our antipodal grasping pipeline and now use mask RCNN to basically, pick up the mustard bottle instead of pick up the arbitrary bottles. Yeah, sorry.
No, I think we didn't mention how the model outputs the masking for this slide. Is it like a union of different squares as we shrink down or manage the layers after cooling? Or is it like it outputs a bunch of points that connect the masking?
It's an image. It's an image with a probability of being occupied, basically, and then you threshold. Yep. Yep. You assign a value to each pixel for the last layer. All right, so this is our task. Picks up, you're looking at a random bin, pick up the mustard bottles, okay? And this is the output of mask RCNN. Let's just play with it for a second here, okay? So it's in your notes if you want to play with it. So it actually comes in a few pieces, right? So I'll make that bigger. I have one Pi file that'll just generate basically the random cluttered scenes. It just generates the images, writes them to disk, okay? I just generated 10,000 random images just by picking a random subset of the YCB objects, dropping them into the bin, waiting till they settled, render the camera from above. Okay? Did that once, haven't done it again for a while. Okay? Training, and this is actually almost straight up out of the notebooks from Torch Vision, right? You can basically just take the example code and adapt them extremely easily. I mean, much to their credit. And you can run it all on Colab, and you basically just, small change to their code, and it works incredibly well. Okay, so I won't run that now because that would take a while on this machine. Okay, so we're just going to do inference here now, and I'll download the model. So the data set that I generated, the 10,000 images at whatever resolution I picked here, I don't know, it was about a 200 megabyte data set. The model itself is about 150 megabytes, right? Which is you know, this is essential, right? And so I think you have to understand that these things are successful, I think, largely because they're in a very in the over-parameterized regime, right? They're using, it's not dramatic compression, it's potentially overfitting, but there's a lot of deep learning theory that talks about why that is actually important to the success of changes the optimization landscape. Okay, but these are massive models, and they got bigger and bigger and bigger, of course. All right, so for those of you that read PyTorch code, this is roughly what the architecture looks like, right? So there's the backbone, and then a pretty simple output layer. I'll evaluate it on a handful of images here. Okay, here's a random image in the data set, and the test set, by the way. And here are the top few segmentation outputs. So this is not restricted to mustard. This is just saying, show me all of your detections. Each one of those detections will have a segmentation, a bounding box, and a label, right? So if I want to use this later for finding the mustard bottles, I'm going to look through the list of outputs, find the one that was labeled as mustard, right? And then use that. Okay. So it looks something like this, right? It completely missed the Cheez-It box. The standard answer is that I just didn't make enough data, right? So, and which is actually a powerful answer, right? The fact that if you see a mistake, you could just label this image, throw it back in the data set, and expect it to probably not make that mistake again, right? That's an extremely powerful thing. Like, a lot of tools don't have that property. If your antipodal grasp is not working or whatever, it's not as simple to fix as just like, oh, I'll just label that one, throw it back in the pipeline. Okay, but it did completely miss the Cheez-It box in this case. Probably I didn't have a lot of examples like that. The region proposals were sort of all over the place. I can only plot a few of them, but they weren't actually as good as I expected. They're kind of all over, but it still managed to dial in those results. And the labels are right on, right? So let's try another one here. So the test set was between, I guess I used mostly training data here, but okay. Bunch of spam cans. It's pretty darn good. Wow, right? So potted meat, it's not called spam in the data set, it's potted meat. Okay, but it nailed that. Right? So I really think this is viable now. I mean, that required an hour of generating images, a couple hours of training, I think, and maybe even less. And then now I've got a perfectly good instance segmentation. Super, super good. So if you do want to throw that into your project pipeline, I do think it's viable. Yeah. Yeah, so the input in the data set is the image, right? And then the output labels that you have to give it are the bounding box for every instance, the label for every instance, and the segmentation for every instance, right? So I think I did so I have the ground truth labels, and I just would actually find the big, I would do the naive thing to compute the bounding box. And it did that in the label generation. Yes?
Let's say you want to take this into the real world. Is there a tool on Drake where you can, when you're generating
Yeah. So the lighting parameters are all there and exposed. Actually, even as I was saying it, I think we probably don't make it super easy to change the texture maps. It's all possible, It's just you have to like, dig in a little bit to change them. We should really make it so it's just like, apply this crazy randomization and just make that super easy. Yeah. Adding more objects and occluders. People will often do that in post-processing. So you'll take your images and you'll just splat other bitmaps on top of it instead of, you wouldn't want to use the physics engine for that. Yeah. Yeah, if that's useful, I could probably even make that easier. But I could certainly show you how to do it today, but I could probably even put a little thing together that would make it easier to do. Yeah.
So why are the region proposals not work as expected?
Well, so it's a couple things. So first of all, I showed that it makes a lot of region proposals, and I rendered like, 20 random ones. So the ones I rendered, presumably there are some that are better than that. I was just, it's just a kind of casual observation that some of them look kind of ridiculous, and I didn't expect to see that. So there are enough good ones that it's very successful, and those are the ones that get trained, and probably more data would, or asking it to do more things. It could also be that just the task was too easy and it didn't need all of the region proposals that it was capable of generating. Yeah. I had hoped to have a cool visualization there. I was like, that's kind of a throwaway visualization. So. Okay, there's a few things that have just dramatically changed in the last couple of years, right? I mean, basically every month. So I'm going to spend time this weekend cleaning up the notes and trying to make them as good as I possibly can for this year, and they will be obsolete in a month, maybe 2 months if I'm lucky, So it's kind of like a labor. I feel like Atlas, or Sisyphus or something like this, right? Okay, so I think Sisyphus is the one I wanted. All right, so big things that happened, right? So ImageNet pre-training, it's still used today, but the features you get out of ImageNet are limited to the ImageNet data, and 14 million images is pretty good. It's clean data, it's curated data, but people wanted to go bigger with their pipelines, okay? And self-supervised learning has been the way that's happened, right? So I think the simplest example of self-supervised learning, maybe the most comprehensible is you think about, I'm typing in my Gmail and it's making a prediction of what I'm about to write, and then I immediately give it the answer, right? Just by completing the sentence, I've not only given it the training data, I've given it all the training data I need. I didn't need to pay a labeler to do this, right? Just by writing email, I've labeled the data. So self-supervised learning, it sounds a little mysterious. It's really just clever ways to extract things from the data you already have that are sufficient learning objectives, okay? And people will call different things self-supervised or not, okay? But GPT is just doing that, right? And we know how powerful it is, right? So it's doing next token prediction, right? Next word prediction, basically. The analogy for image, you could imagine going through the pixels of an image and just trying to predict the next pixel in the image. That probably could work, and people have done things like that with VITs, okay? But the slightly better analogy, which happened in large language models also, is to think about a variation of that, which is to do masked language modeling, right? So instead of predicting the next word, just hide some of the existing words and see if you can complete that. And that one seems to have a better analogy to images. So if you look at some of the common self-supervised image computer vision pipelines, they will do things like cut out parts of the dog and ask it to fill in. This is an easy way to make your own training data. Take all the images online and just apply a handful of different permutations to them. And you know what the right answer is because you've applied this permutation. So you know that it's just a dog that's rotated. You know by pulling this out that it should still be a dog. All these different permutations that you can do. SimClear was kind of it was fun because it just felt like they sort of tried everything and said these are the handful of permutations that sort of worked most effectively. Right, so take your initial input data, apply all the different permutations, and that gives you enough to somehow just automatically train without any human labels required. Now the task, the initial task of just saying like when two images are the same or when two images are different, that's not the final task you care about, but since we know about fine-tuning, then this still seems to give us rich enough representations at this layer that if we pull off the head and then apply that to a new domain, then those features learned to accomplish this trivial task seem to be extremely good features for downstream tasks like instance segmentation. Right, there's a variety of different self-supervised pipelines for computer vision. This is the one that's most analogous to the language models. Maybe if you think about holding out lots of the image and then trying to auto-complete the image with a masked autoencoder. That's, I think, another effective one, right? So you're going to throw away the decoder at the end. You trained this on a task you don't care about, but the goal was to find a feature layer that could be applied to tasks, fine-tuned to tasks you do care about. People have clever things for, for monocular depth, for instance. So you could take two cameras and try to, and compute stereo depth, and then just throw away the extra camera, and now you have a monocular depth camera, for instance. And maybe the current approach that seems to be getting to where we're starting to think of these things almost as foundation models for computer vision. Dino, I think, is the current. People agree Dino is the best right these days for large-scale pre-trained features, which you can then fine-tune to your favorite task, right? And they're pretty clear that in they say in the paper that things like the major contribution to this paper was just figuring out how to scale it to massive, clean data sets, right? So they applied this at a bigger scale, and the training was just a contrastive training, but then the features can be used for lots of downstream tasks like depth estimation, semantic segmentation, instance retrieval, matching, and other things like that. Okay, so I think self-supervised learning has just been a major change in the way people pre-train their feature representations. The other one, of course, which is, I think Dino v2 is getting close to foundation models, but people have been inspired to try to make the foundation models for computer vision, right? CLIP, which many of you in CIM read the CLIP paper early on, right? CLIP is just this massively successful. I think compared to how often it's used, I feel like its citation count isn't quite as high as it should be. But every other paper that has like million citations has a CLIP embedding inside it, right? So CLIP was is still one of the major ways to take text encodings and image encodings and pair them up so that if you want to do visual question answering or anything that's got vision and language coupled, then you tend to use these CLIP embeddings as your intermediate layer to put into the rest of your network. But and these can work out of the box to do sort of where traditionally, everything I said so far, MaskRCNN, for instance, I would have to do fine-tuning to work on my kitchen or my YCB objects. CLIP features work kind of out of the box for pretty darn good segmentation and detection. And the new one that I think maybe has dethroned MaskRCNN is segment anything. So nowadays, it's not clear if you have to fine-tune your data set anymore because we have out-of-the-box segmentation that's shockingly good with segment anything, okay? So segment anything tried to follow this foundation model trend and said we're going to change the segmentation task. Now we're going to say you give me a few clicks in the image maybe a bounding box, maybe a actually, colored label of relevant pixels, maybe a clip-embedded text prompt, okay? And then, of course, you're going to give me an image, and they're going to put out a valid mask. So the cat with black ears, click over here, and it's going to try to put out a valid mask. Actually, it puts out 3 valid masks, right? Which is a pretty different way to think about it than the mask-RCNN case, where you're going to put out the recognition label. Now this is like a much more open semantic, right? I can write anything here and always expect it to try to get a valid segmentation out. And the theme has been of foundation models in generally is not only to have models that can work sort of zero shot with no training on new data, but also models that replace fine-tuning with prompt engineering in some sense, right? You want to have a conversation with this thing. If it detects the wrong, if it colors the wrong thing, then you're going to click again or write more into the prompt in order to refine the answer. And I think fine-tuning is roughly being replaced by prompt engineering. Right, so this came out, and like every robotics group everywhere was using it 2 days later. Right, it works incredibly well. I think most of the things that come out, you kind of say they work incredibly well on Flickr data, right, on web images, but you point them at your robot data and they don't work. That was like last year. That's what you'd almost always say, is that these things don't work on robot data. But now, Segment Anything was really the first one I heard people saying, oh, well, that worked on my robot data. Almost always. So same thing I just said, it outputs 3 valid masks so that you can have sort of multi-level things. The example they always talk about is that if you click on my shirt, maybe you meant me, the person, maybe you meant my shirt, maybe you meant, I don't know, all people like me in the room or something like this. There's often, they said 3 levels of segmentation often do the job. So the whole scissors, the handles, or maybe just that particular handle. How many people have tried Segment Anything? Yeah, it's success. Yes, right? It's pretty good. So there's a live demo you can try online. And they have their curated images. I don't know, let's pick one. So if I click here, it immediately segments that. But if I say, no, actually I wanted, those things, maybe I click again. I thought I would eventually get all the chairs, no? I didn't try this one before. Well, that's not the most impressive I've seen, but maybe, is that a user error or is that a model error? All right, I took a couple pictures when I was walking over here. Just on I thought, oh, I'll take a picture in the room, and then I'm like, there's nothing interesting in the room. So I took a couple pictures as I was walking over. Let's see. Does it not open those? Oh, I outputted from, yeah. I will, rather than show you all my family photos, I'll just unplug for a second. All right. I took a picture of Spot. I had Spot's like dead, waiting for its batteries to be charged. I just wanted to see if it would do, how it would do on Spot here. Oh my God, that's amazing, right? That's perfect. How many pictures of upside down robot dead dogs has it seen, right? That's shockingly good. There's like a Cheez-It box over here. I should probably undo that one. How do I reset? I forgot. Reset. Yeah. Cheez-It box over here. Yeah. I mean, you can just use this thing right out of the box, pretty much, right out of the gates. All right, we try. I tried to find some interesting things as I was walking here. Like, what is that? This data center is like pretty. What's that? You don't think so? I don't know. Well, shockingly good, right? Okay, that's not perfect, but it's pretty darn good. Look at that. That's amazing. All right, there was like a bike rack that had crazy. Yeah, okay, let's see. It's I think out of the box, this thing is like incredibly good. Okay, so maybe you don't need to do fine tuning, and maybe the MaskR CNN is a little bit, you don't. It's not needed anymore. Um, interestingly, even though Segment Anything is is trained on text inputs, the actual API they released, or the model they released, doesn't actually accept text inputs. But it took like, I don't know, 12 hours for people to release packages that called Segment Anything I mean, it's easy to call a visual, anything that does object recognition and then plug it in, the output of that into the Segment Anything. So grounded Segment Anything is the one I think people are using the most. I'll put a link in the notes. But yeah, you can't actually just use SAM if you care about calling a specific object. You'd have to do something else to do the object detection. But it's like shockingly good out of the box detection. Yeah, any questions, any thoughts about that? So it's funny, if you talk to people in the computer vision community, I mean, I think everybody's happy that this exists, but some people are like, it's a little disappointing that they did it by just paying a lot of people to label a lot of images, right? Now they did it with a clever thing, right? So they increasingly people they call it their data engine, right? So they had an initial Segment Anything model, they labeled the segments, and they asked people to correct whatever. And then after it got so good that they weren't correcting, they're like, okay, label the things it didn't label. So it started off, it would just label a few of the most interesting objects. Maybe it would label the bikes, but not the trash or something like this. And then people would go in and they'd fill in more and more details. And they went through cycles of this until they've got they also released the data set, by the way, which is now this like Segment Anything 1 billion, which is a billion image. It's 11 million images, but a billion labels, something like that. Don't quote me on those numbers, but something like that. And they were all expert annotators that would go in with a brush and fix things up and make them as beautiful as they are. So I do think curated data seems to still be important, both in Dino V2, that was a theme, and Segment Anything, this having nicely curated, clean data. You have a question?
Yeah, I was just going to say, like, I used it in intravascular
Okay.
which it definitely
Yeah.
hasn't been trained on that. It's like a new tool, and it worked really well in catching like different types of traumas.
Traumas even?
Trauma.
Okay. Yeah, yeah.
Blood.
Yeah, blood clots. Okay, so he says, yeah, you said intercardiovascular data, it found blood clots out of the box with no training, right? Which is pretty crazy. I mean, there's a notion that if you get enough data, it becomes more, instead of memorizing everything, it becomes more efficient to learn fundamental elements of images and stuff like this, right? So people have explanations, slightly hand wavy, of why these things can do what they can do, but it's still shocking. Yeah.
Yeah, for what it's worth, I spend an obscene amount of my time doing rotoscoping for videos, like rotoscoping where we cut out people.
Okay.
The old system used to be was you had to do it by hand. That then slowly improved to be a more brush-based approach in After Effects. Then Runaway AI came with an AI version which looks similar to that. But that is like worlds above that. It's like hours and hours of video.
Yeah, that's amazing.
I would be interested to see if they can do moving images, and if they can keep an image in place as a
So I don't think they claimed to do it, but I think it was, again, like maybe 24 hours after that someone released Segment Anything and Tracking. Sam, what's it called? Track Anything, of course. Yeah, yeah. Good. Yeah. And is it pretty good, right? I haven't played with it myself, but it's pretty good, right? Yeah. I don't think it was an accepted by peer review paper, but it might have been on arXiv. It was on Hugging Face, you know, probably a week. I'm slightly exaggerating, but not by much. It was like within a week or something, right? Yeah, yeah. That's good. Yeah, no. So, yeah, things are changing fast, right? So, should I write the notes or should I not, right? But I do think at some point we're going to have foundation models that are kind of locked in and useful. I mean, they'll continue to get better, but maybe the technology will be a little bit more stable. We'll see. Okay, so that was sort of like how would you use a generic computer vision pipeline for robotics, or mostly just getting up to speed on the computer. So next time we're going to talk more about like the more robot-specific examples of like what are the features that you care about that the computer vision community doesn't care about. Although that's a little bit blurred now because the computer vision community ran out of problems and started solving our problems too, which is good. Okay, I'll end a little early and we'll see you next time.